So, as we look at vertex form, all of these have a value of a that's equal to 1 or negative 1, okay? So there's no stretching or shrinking going on here. But just noticing here, x minus 2 squared is one we just looked at, okay? It's just the parent function shifted 2 units to the right. So which graph does that go with?
C.
It goes with C, all right? So 1 goes with C. Right. Number 3, what happened to the parent function here?
Translated 3 up.
Yeah, it's just translated 3 units up. It's x squared plus 3. So that one would go with B. All right? So we've got number 3 is B. Okay? Numbers 2 and 4, there are a couple of things going on with each of those. What does the 3 do on number 2?
Bring it up. Bring it up.
Brings it up 3. And then what's the negative in front of the x squared do? Reflects it how? Over the x. Okay? Notice the entire x squared is being made negative. So that's a reflect across the x-axis. Alright, so it's moved up 3 and it's reflected down. That's D right here. Okay? Do it. There we go. Alright, and then our last one. Again, the entire thing that it's being squared is being multiplied by a negative 1, so it's a reflection across the x-axis. And x minus 4, what does that do? 4 units to the right. Okay? So, what haven't we used? We haven't used blue. Okay? So, that's why 4 goes with A. It's shifted 4 units to the right, and it's going down instead of up. Okay? So guys, if you understand what we were talking about in section 4, this stuff is easy. The vertex form is really easy. Okay? Now, question. How would we convert, if we were given an equation in vertex form, how would we convert it to standard form? What, Rachel?
Basically orders of operation.
Exactly. Use your orders of operations. Square the x minus h, whatever that is. So you'd FOIL it out, distribute A, combine like terms, okay? That's the easier way, okay? If, however, we want to convert from standard form to vertex form, we need a little bit more of a process. Does anyone know how we would do that? Or what process we would use?
Quadratic something.
Okay.
I know what it drew.
Okay. Do you remember what the name of that process is? Where we take something that looks like this and make it into something that'll factor.
With like the b squared over a or something like that, right?
Yeah, you're on the right track. What?
Completing the square.
Completing the square, okay. Quadratic formula we could use to get zeros. That's where you set this equal to 0 and that's negative b plus or minus square root, all that stuff, okay? It's related. Actually, completing the square is the process that the quadratic formula is derived from. If you did completing the square with all the a's, b's, and c's left in it, you would get the quadratic formula at the end. All right, that's where it came from. Okay, but let's take a look at our process of completing the square. And I want to show you 2 kind of alternatives to how to handle when this number here is not a 1. Okay, the process is super easy if you've got a 1 there already. There's a little extra level of complexity I don't know why that went. There we go. There's a little extra level of if we have something that's not a 1. Okay? So I'm actually going to create a copy of this, and we'll do it 2 slightly different ways. Now the way I have listed here the steps is the way I prefer. I think it's a little bit easier this way. I know if you've come up through here and you've learned this in like Algebra 2 or something, I know other teachers use the second way that I'm going to show you. So I'll show you both, and you can pick whichever one makes the most sense to you. Personally, I like to get my constant term and this 3 out of the picture completely while I'm trying to complete the square. It's a couple extra steps, but it helps avoid some careless mistakes. Alright? So the first thing I would do is get C on the other side by adding, in this case, adding 6. I'd have y plus 6 equal to 3x squared plus 18x. Alright? And then I'm going to get a equal to 1. So how would I get this 3 to be a 1? I'd divide everything by 3. Okay, so I'm going to divide this by 3, divide this by 3, and divide this by 3. Okay? Now, like I said, this is a couple extra steps, but I think it can help avoid missing, making some little mistakes. Alright, so we have y over 3 plus 2 equals x squared plus 6x. Okay? Now, understand here, I've got a y over 3, or f of x over 3. We're never going to leave it that way. But for now, it's out of the way. Okay? So we can just focus in on this. Now, I want you to understand what we're trying to complete. Completing the square means we're trying to take this and make it into a trinomial that will factor into something squared. Okay? We're trying to complete a perfect trinomial square. That's what that's called. Okay? So we need to add something, and if we add it there, we're going to have to add it over here as well. Okay? So, the question is, what do we add? That's where this right here comes in. Okay? So, we're going to add b over 2 squared to both sides. Now notice, I'm not talking about the original b, I'm talking about the b I currently have. So that's 6. Alright? So good. I'm going to take 6, divide it by 2, and square it, and I get 9. So I'm adding 9 to both sides. And the whole point of doing that was so it would factor into x plus 3 squared. Okay? That was the whole point of doing that. The one nice thing about this, even if you end up with some fractions and things like that, don't think too hard on the factoring. It will always factor into an x and then whatever half of this is, including the sign. Alright? So if it were a minus 6, we'd have x minus 3. Okay? So, that equals now a y over 3 plus 11. So all I have to do at this point, here's where this method does use a couple extra steps. I need to get rid of the 11 and the 3, so y is by itself. Okay? So I'll just subtract 11 from both sides, and I get y over 3 is x plus 3 squared minus 11. And then I'm going to multiply everything by 3. So y would equal 3 times x plus 3 squared minus 33. Okay? So don't ever leave it like this. Always get the y back by itself. But we at least didn't have to worry about the 6 or the 3 as we were trying to figure out the other side. Okay? Any questions so far? Alright, let me show you the other way. Okay? The other way is to leave the 3 and the 6 on the right side of the equation, but what we're going to do with them is we're going to take the 3 and we're going to factor it out, but we're only going to factor it out of the first 2 terms. Okay? And we're going to leave that 6 kind of separated off to the side. It's still there, we're just kind of ignoring it for a minute. Now we go through the same process. We use that 6 here, and we're going to take 6 over 2 squared. Alright, so 6 over 2 squared is 9 again, and we recognize that we need to add that to make this a perfect square trinomial. Alright? But this is where the part that people often mess up is. Okay, so this is why I prefer the previous method, but if you're careful, this method is faster. Alright? So, what did I actually add to this side?
27.
I added a 27. So, exactly. So to balance it out, we need to subtract 27. So here I added 27, 3 times the 9. So when I subtract 27, I really just added 0. So I didn't change the problem at all. Okay? Does that make sense? Okay. At this point, we just factor, combine these, and you've got your minus 33. You end up with the same answer. This one took about half as many steps, but you had to be really careful of, because a lot of people will just say, oh, I have a plus 9, and they subtract 9, and then they mess up this value here, the 33. Okay? So just be really, really careful with that. All right. Any questions about completing the square? All right. The second thing I want to look at today is a strategy for optimization, and I'm really covering this mostly just so that all of us have our terminology down. We all understand what we're trying to do and have at least a good general strategy for handling these kinds of problems. When we're talking about optimization or optimizing something, we're trying to find the optimal solution. This is all talking about the same thing, and what we're talking about is finding the best possible solution. Okay? Now, the best possible solution may be defined differently depending on what the situation is. It may be the highest value, like if we're dealing with what?
Money.
All right. What kind of money?
Like earnings.
Okay, earnings. If we want to maximize our revenue or our earnings, or we want to maximize our profit, okay? That would be something where the highest value is going to be the best solution. What's a case where the smallest value would be our best solution? What?
Debt.
Huh? Well, golf. Okay, yeah. What'd you say?
Debt.
Debt? Alright.
Spending.
You're spending, okay? You want to minimize how much you're spending on something, or you want to minimize how much debt you're going into. That's where your lowest possible number is going to be the best solution. Okay? So you have to look at the situation and ask yourself, am I trying to find the highest value here, or am I trying to find the lowest value here? Okay? Now, here's a basic strategy if you're trying to deal with an optimization kind of problem. Alright? First of all, of course, after you understand what the problem is saying and all of that basic stuff that applies to all problem solving, you're going to try to write a function where your dependent variable, that's the y, right? The dependent variable is the value you want to optimize. Okay? And that dependent variable is going to depend on some independent variable. Okay? So we might have revenue, and it's based on the price of the item that we're trying to sell. So we're going to write a function where the revenue is the dependent variable, and it depends on the price that we're selling each unit at. Okay? The second step is one that students often overlook. We want to determine the domain for the situation. Now notice I didn't say the domain for the function. In quadratics, our domain is always all real numbers. Okay? However, in the situation, we might not be allowed to have fractions, or we might not be allowed to have negatives. Okay? Or the range may be that we can't have negatives. Okay? And if our dependent variable can't be negative, that obviously would then limit what our domain could be. Okay? So, once we've figured that out, then we want to find the max or the min, depending on what best means in this problem, within that domain. Okay, and that'll give us our optimal solution. Okay? In quadratic functions, what's the max or min always going to be? It's going to be the vertex. Okay? It's going to be the vertex. So it's going to be important that you understand how to find the vertex a number of different ways. Okay? If you're given standard form, or I'm sorry, vertex form, it's right there. It's h and k. Alright? If you're given standard form, remember h is your negative b over 2a. Okay? If you have trouble remembering that,